Imagine a bomb so sensitive that a single particle of light will set it off. You can't touch it, you can't look at it, any interaction, and it explodes. But you need to know if it's live. Quantum mechanics says there's a way. You send a photon toward the bomb along two possible paths. The photon never touches it. The bomb never explodes. And yet, somehow, you learn it's live. You detected a bomb using a photon that was never there. If that sounds impossible, good, because it gets worse. Much worse. Albert Einstein once said he liked to think the moon exists even when nobody looks at it. That feels obvious. Completely obvious. Of course the moon is there. It was there before humans existed. It'll be there long after we're gone. But a century of the most precise experiments ever built now says something different. We literally cannot prove the moon exists when no one observes it. We can't prove anything exists when no one is looking. And the chain of evidence that leads to this conclusion starts with an accident in a basement laboratory in 1927. Clinton Davison and Lester Germer were shooting electrons at a nickel target in a Bell Labs vacuum chamber. Routine experiment, nothing special. Then the equipment overheated. The nickel recrystallized into large, single crystals, and the electrons started behaving like waves. They diffracted. They made patterns that only waves should make. Nobody predicted this. Nobody wanted this. Electrons were particles, solid, definite, real. Except now, they weren't. This accident earned Davison a Nobel Prize in 1937. It also opened a fracture in our understanding of reality that has never healed. Matter, the stuff that makes up your body and your furniture and every solid object you've ever touched, turned out to behave like a wave under the right conditions, and nobody could explain why. But the worst consequence of that fracture was still 90 years away. Two Swiss physicists would eventually prove that the problem isn't just strange, it's terminal. 62 years after that overheated lab, a physicist named Akira Tonomura at Hitachi built the most precise version of a legendary experiment. He fired single electrons, one at a time, through two narrow slits. Each electron hit the detector screen as a single dot, one dot, then another. Perfectly normal. But as thousands of dots accumulated, they formed a pattern, an interference pattern. Waves make that pattern when they pass through two openings and overlap. Each electron traveled through both slits simultaneously. A single particle took two paths at once, and here's what broke people. When Tonomura added a detector to watch which slit each electron chose, the pattern vanished. The electrons behaved like particles again. The act of observation destroyed the wave behavior. Two Swiss physicists would later prove this problem is even worse than it sounds. This result horrified Einstein. At the 1927 Solvay conference in Brussels, he refused to accept it. God does not play dice, he told Niels Bohr. Bohr fired back that Einstein should stop telling God what to do. A 30-year intellectual war began. Einstein spent the rest of his life trying to prove quantum mechanics was incomplete. He designed thought experiments to trap it in contradictions. Bohr defeated every single one. Einstein died in 1955 without proving his case, but his failure mattered. It mattered enormously. Because every objection Einstein raised forced physicists to make quantum mechanics more precise, and that precision would eventually reveal cracks far deeper than Einstein ever imagined. His stubbornness, his refusal to accept the theory on faith, became the engine that drove quantum physics forward for the next century. In 1935, Einstein made his most famous challenge. He published a paper with Boris Podolsky and Nathan Rosen describing two particles created together and sent in opposite directions. Quantum mechanics predicted that measuring one particle would instantly determine the state of the other, no matter how far apart they were. Einstein called this spooky action at a distance. He meant it as ridicule, as proof that the theory was broken. Something had to be carrying information between the particles. Some hidden variable the equations missed. The universe couldn't possibly work by magic, but Einstein had accidentally described something real. The correlation wasn't a flaw in the math. It was a feature of nature. The particles really were connected across any distance instantly with no signal between them. And his philosophical question about the moon became a testable physics question. Does the particle have a definite state before you measure it? Or does your measurement create that state from nothing? Now, back to that bomb. In 1993, two physicists named Avshalom Elitzur and Lev Weidman figured out how to detect it without touching it. The trick uses a device called a Mach-Zehnder interferometer. You split a single photon onto two paths using a half-silvered mirror. Both paths recombine at a second mirror, and the photon exits toward one of two detectors. When both paths are clear, the photon always hits detector C. Perfect interference guarantees it. But place a live bomb on one path and everything changes. The bomb's presence collapses the superposition. Now the photon can hit detector D. If detector D clicks, you know the bomb is live. The photon never touched it. The bomb didn't explode. Anton Zeilinger's group demonstrated this in 1994. Success rate 25%. 1 in 4 times you learn the bomb is live without triggering it. The other times, either the bomb explodes or you get an ambiguous result. 25% might sound low. But remember, the alternative is certain death, and with advanced quantum techniques, that success rate approaches 100%. Think about what that means. The road not taken left footprints. A photon that could have gone one way, but didn't still change the outcome. Things that didn't happen had physical consequences. This isn't philosophy. This is experimental data. The ghost of a possibility, the shadow of a path the photon could have traveled but never did, that ghost altered the result at the detector. Counterfactuals are real. Events that never occurred shape the events that do. If that's true for photons and bombs, what else does it apply to? And if observation changes outcomes with bombs, a deeper question waits. What if observation doesn't just reveal reality? What if it freezes reality in place? 2,400 years ago, a Greek philosopher named Zeno of Elea asked a simple question about an arrow in flight. At any single instant, the arrow occupies a fixed position. It isn't moving at that instant, it's just there. But if at every instant the arrow is still, when does it move? For millennia, this was just a clever puzzle. Then in 1977, two physicists named Misra and Sudarshan showed that quantum mechanics has the same problem. And in the quantum world, it's not a paradox. It's a prediction. If you measure a quantum system frequently enough, you can prevent it from changing. The arrow really does freeze. Not as metaphor, as measurable physical fact. Watch a quantum system closely enough, rapidly enough, and it cannot change its state. It stays frozen in the present moment forever. And someone was about to prove it in a laboratory. In 1990, a team at the National Institute of Standards and Technology trapped individual beryllium ions with lasers. These ions were supposed to transition between energy states. That's what quantum systems do, they evolve, but the researchers fired laser pulses every few microseconds to check the ion's state. Each measurement reset the ions back to where they started. They couldn't change, they couldn't evolve. 16 years later, the Kettler group pushed this further. They worked with rubidium atoms cooled into a Bose-Einstein condensate. Transition rates dropped to 0.5% of normal, 200 times longer lifetimes than expected. Observation had become a cage. Reality froze under the weight of being watched. A quantum system that should have decayed in microseconds lasted 200 times longer, not because anything physical restrained it, because someone kept checking on it. The act of looking held it in place. But here's the twist nobody expected. In 2001, Mark Reisen's group at the University of Texas at Austin discovered the opposite effect. Measure at a different frequency, and you don't freeze the system. You accelerate its decay. Observation doesn't just stop change, it can speed up destruction. The universe responds to being watched. but the response depends on how you watch. Einstein wanted reality to exist whether you look or not. It turns out reality changes based on when you look, how often you look, and at what rhythm you look. The observer isn't passive. The observer is part of the experiment. The observer isn't a bystander. The observer is a participant. And the next discovery would make this feel almost tame by comparison. In the year 2000, a team led by Yoon Ho Kim built an experiment that seemed to break time. They created entangled photon pairs using a special crystal. One photon, the signal, hit a detector immediately. The other, the idler, traveled a longer path and arrived 8 nanoseconds later. When the idler's path preserved which-way information, the signal photon showed no interference, normal. But when the idler's path erased that information, interference fringes appeared in the signal photon's data. The signal photon had already been detected. Its fate was sealed. Then a measurement on its partner, 8 nanoseconds later, seemed to reach back and rewrite what the first photon did. The math says causality is preserved. The correlations only show up in sorted subsets. But the raw experience of this experiment is pure vertigo. It feels like the future reached back and rewrote history. Picture it this way. You take a photograph and you develop it. The image is fixed. Then someone in another room makes a choice, and your photograph changes. Not the interpretation of the image, the actual content. That's what this experiment feels like. And it connects back to the bomb. Things that didn't happen affect reality. Now add this. Things that haven't happened yet might also affect reality. The past and the future conspire through quantum correlations in ways that classical physics never imagined. The two Swiss physicists and their 2018 paper were getting close. But first, reality needs to break one more time. And this time, it breaks cleanly. A physicist named Lucien Hardy found the cleanest break in 1992. He imagined an electron and a positron entering separate interferometers that overlap at one point. If both particles take the inner path, they meet and annihilate each other. Simple logic says the two output detectors can never both click. If both particles arrived at their detectors, at least one must have taken the outer path and avoided annihilation. Hardy calculated the quantum prediction. Both detectors click simultaneously with a probability of 1 in 16. Experiments confirmed it to 5 standard deviations of certainty. 2 people walking toward each other in a hallway. If both are there, they collide. They exit from opposite ends. Neither took a side door. They were both in the hallway. They didn't collide. Logic refused to hold. Hardy called this non-locality without inequalities. He didn't need statistics or bell curves to show the universe violates common sense. Pure reasoning was enough. The universe is not obligated to be logically consistent by human standards. And that fact opens a door to the strangest question of all. Eugene Wigner understood this territory better than most. He fled Hungary as the Nazis rose to power. He worked on the Manhattan Project. He won the Nobel Prize in 1963. And in 1961, he asked a question that still has no answer. Imagine your friend is inside a sealed laboratory measuring a photon. She looks at it and sees a definite result. The photon is polarized upward. She knows this. It's a fact to her. But you stand outside the lab. Quantum mechanics tells you to describe your friend and the photon together as a combined superposition. She hasn't decided yet. She's in both states. Whose reality is correct? Wigner briefly believed consciousness itself collapses reality. Then he retreated from that idea and called it absurd. The question outlived his answer by decades. It sat there unanswered for over half a century. Most physicists treated it as a curiosity, a philosophical toy. They were wrong. In 2019, a team at Heriot-Watt University in Scotland finally tested it. They built an extended version of Wigner's thought experiment and ran it with real photons. 2 observers recorded their results. The results contradicted each other. Both were correct. Published in Science Advances, the paper confirmed there is no single objective reality that both observers share. You look at a coin, and it's heads. You know it's heads. Someone outside your room says you haven't decided yet. You're still in superposition. Neither of you is wrong. This is not a thought experiment anymore. This is laboratory data. Two people can look at the same physical system and see contradictory facts. Both can be right. There is no tiebreaker. No deeper layer where one answer wins. Reality itself is observer dependent, and it leads directly to the paper that shook everything. In 2018, Daniela Frauchiger and Renato Renner at ETH Zurich published the result that had been building since 1935. They set up a thought experiment with 4 agents. 3 assumptions, all of them reasonable. First, quantum mechanics applies to everything, every system, every observer. Second, different observers should agree on physical facts. Third, measurements produce definite results. Frauchiger and Renner proved with mathematical certainty that all 3 cannot be true at the same time. One agent follows the rules and concludes heads. Another agent follows the same rules and concludes tails. Both reasoned correctly. Both used the same physics. The answers contradict each other. Imagine a legal system where 2 judges apply the exact same law to the exact same case and reach opposite verdicts, and both are provably correct. The law isn't wrong, the judges aren't wrong, the system itself cannot hold together. No one has resolved this. The paper remains actively contested. 5 years later, the best minds in physics still disagree on what it means. Step back and look at the arc. Erwin Schrödinger proposed his cat thought experiment in 1935, a cat in a box, simultaneously alive and dead, until someone opens the lid. That was strange enough. Then Wigner extended it in 1961 and put a human observer inside the box. That was worse. Then Frauchiger and Renner extended it again in 2018 and showed the theory contradicts itself. Each generation made the problem more severe. After 100 years, there is no consensus on what the word measurement means in quantum mechanics. Copenhagen, many worlds, pilot wave, cubism. 4 interpretations. All of them make identical experimental predictions. No test can distinguish between them. This may be permanently beyond our reach. Richard Feynman said in 1965 that nobody understands quantum mechanics. 60 years later, that statement remains completely accurate. The theory works perfectly. It predicts every experiment with flawless precision, and nobody can tell you what it means. A bomb detected by a photon that was never there. A moon that might not exist when nobody watches. These 2 images have haunted this entire story because they point to the same fracture. Alain Aspect violated Bell's inequality by 242 standard deviations in 1982. Anton Zeilinger ran a Bell test using the light from distant stars in 2017, closing every remaining loophole. In 2022, both men shared the Nobel Prize in Physics for proving that the universe is not locally real. Einstein was wrong about the physics. Entanglement is real. Hidden variables don't work. But his stubbornness forced every experiment that confirmed it. His greatest failure was his greatest gift to science. Every objection he raised became the blueprint for the experiment that proved him wrong. And his question about the moon still stands, unanswered. I like to think the moon is there even when I am not looking at it. 100 years of the most precise experiments ever conducted say we cannot prove that it is past.